Thank you for the introduction. And thanks to Shafi and Rich for inviting me and the organizers for having me here. Yes, I do want to talk about this new framework that we have for learning with distribution shift. And this is joint work with my student Stavropoulos and my postdoc Arsen Vasilyan. But really what I want to talk about is this loaded term of generalization. And the first point I want to make is that the dominant paradigm in sort of computer science and statistics, when people say the word generalization, what they mean typically is that, you see you're a learning algorithm, you see some training samples drawn, some usually labeled training samples drawn from some distribution D, and then you want to output some classifier H. Think of just, for the rest of this talk, like H is going to be Boolean. We're going to be thinking about doing classification. And the goal is to output a classifier H that performs well when you take new test samples drawn from this distribution D. Okay, so the point that I'm making here is that usually let me get this right. Usually the distribution that you train on, like D, is the same as the distribution that you test on. Okay, and then what I want to, one of the major points that I want to make in this talk is that this notion of generalization is probably wrong and is certainly not the notion of generalization that people from other fields think about when you say the word generalization to them. So, as I mentioned, this is really like a fundamental area of study in computer science and statistics. It's been studied since the 70s. These notions of epsilon delta learning that I'm sure many of you are familiar with was originally introduced by Vapnik and then later by Valiant. And there are literally thousands of papers, theoretical papers, empirical papers written. And it's still a very important problem trying to understand when you can learn in the case that your training distribution is the same as your test distribution. But I think maybe a better word, instead of generalization, maybe a better term to use is, say, mimicry or imitation. And an interesting question is are we actually doing any real learning when the training distribution equals the test distribution? I think naturally we all think of, when we think about learning and generalization, we'd like to think that you're doing something more than that, or that you're able to generalize sort of beyond the distribution that you trained on. And relatively speaking, there's very little known, at least theoretically, in the case when the training distribution does not equal the test distribution. But that's not to say that nothing is known, but relatively speaking, when we have the case when the training distribution equals the test distribution, I could say something really controversial, like for many modalities, maybe we should even consider this problem solved. After all, if you want to learn a distribution of images, we know how to train a diffusion model, and it will generate new images from the same distribution, and it will do a great job. If you want to, learn the distribution of kind of natural English text, we now know how to train language models, and the language that they generate is excellent. So maybe we should even consider it a quote unquote solved problem, whereas in the other case, we know much less. So in order to kind of illustrate the differences between when the kind of classical notions of dtrain equals dtest versus distribution shift, I wanted to give you an example from protein engineering. So maybe not everyone knows that I lead a group at UT that does protein engineering now. It's a fascinating question. It's really built for machine learning because of all of the data that we have and many of the applications. And in protein engineering, so you're given as input a sequence, like an amino acid sequence. So a protein is just a sequence of 20 different amino acids, all just written linearly. So here I have some sequence that spells out my last name. K turns out to be the amino acid for lysine. I is isolysine, V is valine, so on and so forth. You just have a sequence of amino acids that forms a protein. And in protein engineering, the goal is to take one of these input sequences and to make mutations on this sequence. So to make a handful of mutations, actually change one amino acid to a different amino acid, and then to hope that the function of that protein has actually improved. So for example, if you have an enzyme, which is a protein, and it catalyzes a reaction, maybe you can make 3 or 4 mutations on this particular amino acid sequence and hope that catalysis goes up by like 100x. So there's innumerable applications if you can solve this problem, from creating new vaccines and therapeutics to creating new enzymes, bioengineering. It's a fascinating area. And AI and machine learning models are now being used widely in this area. And the way that these models work, it's very interesting, is they take hundreds of millions of amino acid sequences, and they treat them like sentences. Okay, so they treat them like a language model, and then you do some BERT type training on all of these amino acid sequences. So what you do is you have hundreds of millions of amino acid sequences. For each one, you mask out like 15% of the residues, and then you train a model to predict what amino acids, what residues were masked out. Okay, does the training make sense? It's like a BERT type training on amino acid sequences. And the most common approach is to build a model that does this and then measure something called wild type accuracy. Okay, so what is wild type accuracy? Well, the wild type accuracy of your model is I take a protein from nature that was not in the training set. I mask out like 15% of the residues, and then I just measure how many of the residues is my model able to predict and fill in after I've masked them out. And I do that for all of these proteins that are sitting there in my test set, and I get some measure of how well my model is actually able to predict amino acid residues. That's called wild type accuracy. Okay, and the interesting thing is, so there are many papers written on this. Many people have trained models to do this, and you kind of ask like biologists who are doing this, saying, would you like to have a model that's 100% accurate? Would you like 100% wild type accuracy? And they're like, yeah, give me the model with 100% wild type accuracy. Then you tell them, well, that means that if you take a protein that's found in nature and you mask out some residues, it's just going to give you back the protein that you found in nature. And remember, your goal was to do protein engineering. Your goal was to like make residues, new mutations to make a new protein that does something better. So if your model has 100% wild type accuracy, it's actually a totally useless protein model. And so they go, oh yeah, you're right. I don't want 100% wild type accuracy. They're like, okay, well, do you want 60% wild type accuracy, or do you want 75% wild type accuracy, or 90% wild type? Like, what do you want? And then they start to realize, oh, this is a totally wrong metric. We actually want something that's able to generate proteins that are out of distribution. And we have other models that do other things with respect to protein structures and sequences. And whenever you talk to a biologist or a chemist, when they say like, does your model generalize, they always mean out of distribution. They never are thinking about the case when dtrain equals dtest. And this was very interesting to me. I've worked in theoretical machine learning and theoretical computer science for 20 years. And I kind of realized like, oh yeah, the way that we use the term generalization is sort of wrong. And it's not just biochemistry. I think like the prototypical example for learning with distribution shift really is in AI for health. You could imagine building a foundation model on a bunch of patients where we know something about these patients already. They're in a data set. We know, say you're trying to build a model that detects cancer from MRI scans. We have a bunch of people. We know whether or not they had cancer. You build this foundation model, and then you'd like to deploy it to a new population of patients, right? And so you have this labeled training set, and then you have an unlabeled test set. But of course, there are many stories where machine learning models that were developed for clinical practice completely fail when they're deployed on an out of distribution or a new population of patients. And it's really scary. I think it's probably the main reason why we don't see more models deployed and used in AI for health, because we're just terrified that we've completely overfit to our training set and we have no ability to generalize out of distribution to a new population of patients. And furthermore, we have like no way of even measuring that. So this would be another great application of why learning with distribution shift, probably, in my opinion, is the most important problem in machine learning. Certainly for trustworthy machine learning, if you want to be able to trust your model, we really have no way of modeling this problem, no efficient algorithms for it. Okay, so what I'd like to tell you about is this new way of thinking about learning with distribution shift, and the goal is to come up with efficient algorithms, provably efficient algorithms, where I don't make any assumptions at all on the test set. And I'll come back to that later. And the name of this model is called TDS learning. It's testable. It stands for testable learning with distribution shift. I'll get back to it a little bit later. But it's a model of something called domain adaptation. And for the rest of the talk, I'm going to assume that most people have seen these traditional notions of epsilon, delta, or pack learning. I'm happy to go over it if you'd like me to go over what that is. You want me to go? Okay, sure. Okay, fine. Check this out. See, I can do this. Okay, so like, an epsilon delta learning, you have a learner, you draw samples from some distribution D on like, let's just say it's RD cross -1, 1. So you have a bunch of points and they're labeled +1, -1. And then, with probability greater than or equal to 1 minus delta. So there's some probability you draw all these samples and you just see the same sample over and over again. So there's going to be some failure probability. So you want with probability 1 minus delta, so with pretty high probability, I output a hypothesis H whose accuracy whose error is at most epsilon. Okay, so that's epsilon delta learning. And in pack learning, you want an algorithm that actually runs in polynomial time and all of the relevant parameters. You just want an algorithm that doesn't do something like brute force search over all possible functions in your class functions in your concept class. Okay. Yeah.
I have a question about how does your distribution shift apply to protein generation? Like, if I generate a new protein, how do you there's no distribution there? How do you decide if it's good or not?
Yeah, so that example is sort of one thing that commonly happens in protein. So another problem that we look at is you have a classifier to determine what effect a mutation is going to have on a class of proteins, and you typically train in your training set on like enzymes and structure proteins and transport proteins, and then someone, for example, in our chemical engineering department will come to me and say, I have an antibody that I need you to engineer. And like, oh, okay, I'm in trouble because there aren't that many antibodies in my training set. So it's a problem.
So there's a way to check ground truth?
Well, you can always go to the lab and check ground truth. That's what's great about this area. Of course, it's expensive, but. Okay, so how many people are familiar with domain adaptation, the formal model? Yeah, that's usually what I get, about like 1/3 of the audience. So let me tell you what domain adaptation is. It's a beautiful model. And in this model, so you have this, we separate training from tests. So you have a training distribution D. Again, it's on, points in D-dimensional space, cross -1, 1. And from D, as a learner, you always get labeled samples. You always get to see labeled samples from your training distribution. Think about if you're building a foundation model, you get to generate the training distribution sort of yourself. And then you have this test distribution, D prime. This is like your test this is like a set of patients that have no labels, and you want to run your classifier on these patients and determine, whether or not they have disease. Okay, so you get a test distribution or even just a test set where the learner only sees unlabeled people. Okay, so that's D prime. And then your goal is to output, this is like, really what we'd like is to output a classifier H such that the accuracy with respect to the test distribution, so these new set of patients, I want to be able to classify them well as to whether or not they have disease. Okay, so it's sort of it's different from like the traditional epsilon delta notion. We have both a training distribution where you see labeled samples and an unlabeled test set where you have to perform well on this unlabeled test set. Okay, all right. Okay, and now I have this, you can ignore this slide if you want, but I have this lambda parameter, and lambda measures the error of the best fitting classifier with respect to both the train and test distribution. So you look at the minimum over all functions in some class. Think of your class as like decision trees or half spaces or neural networks of some size, whatever you want. And lambda measures the error. So you take the minimum over all functions in your class, like all neural networks, of the error of that neural network on D plus the error of that neural network on D prime. Yes, you have to take the sum. Turns out this is necessary. If this is confusing, you can assume that lambda is 0 and that there literally is some ground truth like neural network or half space or decision tree that classifies everything correctly in both D and D prime. Okay, but it's the error of the best fitting classifier from C. And then what do we want to do? Well, we want to output a classifier H, and the error of H with respect to this test set D prime, it should be like some constant factor times lambda plus epsilon. So it turns out the best you can possibly do is lambda plus epsilon. You can prove that information theoretically. I'll cut you some slack and I'll let you output a classifier whose error is at most like some constant factor times lambda plus epsilon. Okay, so that is the goal in domain adaptation. question. Yeah.
What does the big O depend on?
Nothing. So it should be like some global constant, like 100. We can actually achieve 1 for many cases. I'm not sure I'll be able to get to it, but good question. Okay, now I have the pleasure of telling you like almost every result in the theory of domain adaptation in one slide. Okay, so essentially every result in the theory of domain adaptation is the following generalization bound. So you fix a classifier H, okay, and the error of H on your test set D prime is at most the error, you can prove, is at most the error of H on your training set, okay, that's good, plus lambda, remember I said lambda was unavoidable, but you can just assume it's 0, plus, and here's the kicker, some notion of distance between D and D prime. And I think intuitively that makes sense. If your test set was drawn from some distribution of patients that like have nothing to do with your training set, then how could you hope to do well? Like the error of your classifier is just going to have to eat that, okay? And so, yeah, so pretty much every result in the theory of domain adaptation is a generalization bound of this form. Okay, and you might ask me like, well, what do you mean distance between D and D prime? Like what is a classical notion of distance between two distributions? Okay, so here's one notion that's probably the most well-studied notion. It was originally defined in a paper by Ben David et al. And follow-up paper by Mansour et al. It's called discrepancy distance. Okay, and it's actually very simple. You just look over all pairs of functions from some class. Like again, think of the class being like neural networks or whatever. So you look at all pairs of neural networks and you ask like, what's the probability that those two neural networks disagree on D minus the probability that those two networks disagree on D prime? Okay, like how, they differ a little bit on D, but maybe they differ a lot on D prime. Okay, well now your discrepancy is very large. If like they differ, by the same amount on D and D prime, so that means sort of D and D prime are sort of close with respect to these all pairs of functions, then we'll say the discrepancy distance is small. And truly, Shafi, you might be interested in this. This means that D prime in this case really is pseudorandom for your function class with respect to D. So it turns out, interestingly, that this notion of distance between two distributions is a sort of a well-known measure of discrepancy from pseudorandomness. So pseudorandomness has something to do with learning with distribution shift, and we'll see that pop up later. Okay, so this is like the prototypical measure of distance between D and D prime. The big point, maybe like the most important point I want to make in the entire talk, potentially, is that these bounds are not useful. And the reason why they're not useful is that these notions of distance are not computable efficiently, okay? So imagine that you actually trained a classifier and you have your training set there with you, and you have these unlabeled points and you have your set of test patients that you want to evaluate it on, and you just want to know like okay, I'm going to apply one of these generalization bounds. I want to understand how well is my classifier going to perform on this test set from D prime. So you consult these papers that have these generalization bounds, and you're like, all right, I know this. Let's assume lambda is 0. I'm not even going to worry about it. And then you have this distance between D and D prime, and you can't compute it. So you just, you could just assume the only upper bound you can conclude efficiently is 1. Okay, so you've really learned nothing. This is very disturbing. I was very disturbed by it. And I guess maybe the meta point that I want to make is something about assumptions in machine learning, and in particular in machine learning theory. And the first thing is that they're everywhere. So for example, if you do compressed sensing, or you're ever exposed to that, thousands of papers on compressed sensing, you have to assume that your design matrix is RE or RIP or something. It's NP hard to test that. Like you can't test if that assumption is satisfied when you want to run your compressed sensing algorithm. If you want to apply all these algorithms for learning neural networks, like they all assume that the covariates are drawn from a Gaussian or a sub-Gaussian density. You can't test that. You cannot test if a distribution is close to a Gaussian. It requires exponentially many, it's not even well defined really, but it requires exponentially many samples in the dimension. So even simple problems like I'm going to test if my marginal distribution is Gaussian, like good luck to you. And this is sort of, this is really because we're looking at an average case problem. This is like, the vexing issue of average case analysis. Like in theoretical computer science, we're used to working in the worst case. You know that your algorithm is going to run in a certain time because you proved it worked for all instances. It's very, we take it for granted. Like, merge sort's always going to work because you proved it's going to work for every single sequence of numbers that you give the algorithm. But like for an average case algorithm, you have to rely on some assumption, or some distribution, or your inputs are coming from something. And frequently you just can't verify that. So you don't know if your algorithm, when you actually run the algorithm, you have, in a way, like unless you can verify the assumption, you have no guarantees on how the algorithm performs. So it's just sort of inherent to these types of average case analysis problems. And that's why I think, like, if you think about theoretical computer science, certainly it's been much more difficult to make progress on average case analysis than it has been, in a way, in worst case analysis. So what I want to point out here is that for the results that I'm going to tell you about, that my group and I have been working on, the big win, in my opinion, is that we're not going to make any assumptions on the test set. Okay, I'm not going to ever assume anything about d-test. We'll make no assumptions, because why should you? I mean, we're so bad at understanding, for example, if you want to deploy, you have a test set of patients that you want to apply a machine learning model to, and someone says, well, how similar is this test set of patients to like the patients in your training set? I don't know. How do you measure that? Like, what if they were from the same state or the same age? Like, is that sufficient to say that they're similar, or should you look at, like, RNA? Should you do RNA-seq on everything? Like, I don't know. It's very complicated. Okay, so back to domain adaptation. So I can actually tell you about some of our results. So remember, training distribution with labeled samples, test distribution with unlabeled samples. You want to output a classifier that does well on the test set. The sample complexity turns out, for those of you interested in Rademacher complexity, it is controlled by the Rademacher complexity. I'm going to skip that. Okay, so finally, we're back to TDS learning. I can tell you what our model is. Okay, so you have a learner, and the first thing the learner is going to do is take samples from both D and D prime, so unlabeled and labeled samples from D and D prime, and then the learner is actually going to run a test. Okay, like an efficient algorithm test on all of the samples that it sees, labeled and unlabeled. And if the test accepts, you're going to get a super strong guarantee. The learner is going to output a classifier such that the error of h on d prime is at most, lambda plus epsilon, exactly what you wanted. And furthermore, you will get a proof that this classifier actually has error at most lambda plus epsilon. No assumptions needed. When the test succeeds, you get a certificate. You get a proof. Okay, now the unfortunate thing is that, like, your test might reject. Okay, but right now, as you can see, like the model is vacuous as I've defined it, because you could just, whenever the learner runs its test, it could just always decide to reject. Okay, so what should really happen here is when, there's this caveat, when the marginal distribution on D train, so restricted to the covariates, equals the marginal distribution on D test, then the test must accept. Okay, with high probability, but whatever. Okay, so this is how we're going to get around these very annoying and difficult notions about computing these notions of distances between D and D prime. We're going to sidestep that issue, and instead we're going to just let the learner reject sometimes. Okay, and this would be, if we had something like this, like you could imagine, it would be very powerful. Like if you had a language model that could say to you, like, I'm not confident in my answer, or like, you should ignore this part of my answer because I know it's bogus. Like that would be great. So I don't think it's so bad to let the algorithm reject. And I think also, when people see this, their first reaction is, well, that's very stringent. It means that your algorithm is just going to reject all the time, say when your distribution is not the training distribution. Actually, I would argue, and I want to try and convince you, actually this is a very powerful guarantee. And furthermore, we'll relax this guarantee. So we'll come up with tests that accept way more often than just when D train equals D test. And the other thing to keep in mind is the test might accept, like in all sorts of scenarios, who knows when. And whenever it does, you get a super powerful guarantee and you get a proof that your classifier works. So any questions about the model? Right, so in this model, we now have like a variety of efficient algorithms. So you and the Kalais and Omar Montasser defined a model like of PQ learning that's somewhat similar to this, but you didn't have any efficient algorithms for it. So the big contribution here is going to be to come up with actually efficient algorithms in this model for a variety of function classes. You needed an oracle for empirical risk minimization, but that's, if you have that, then you can solve NP-complete problems. Okay, so just let's get a feel for let's warm up. Let me give you a feel for this model, and then I'll show you some like algorithms. I'll get to the more interesting algorithms. Just give me a second. Okay, so for people, Encore, you cannot answer this question, but for people who have not seen this before, why is TDS learning more general than PAC learning? Like, why is this a more general problem? Why would this, like, if you had a TDS algorithm, why would it imply a PAC learning algorithm? Yeah.
When dtrain equals dtest, you get the PAC learning.
Yeah, so in PAC learning, dtrain always equals dtest, and you always have to output a classifier that does well. But in TDS learning, when dtrain equals dtest, your test has to accept with high probability, and you have to output a classifier. So it's harder. And the dream scenario would be to take all of our sort of ordinary PAC learning algorithms and translate them or port them into the TDS learning model. Okay, that would be great if we could take everything that we already know in like epsilon delta learning, PAC learning, all of our efficient algorithms, and soup them up so that they can then handle some notion of distribution shift. That would be great. And that is one line of research that, that my group and I have pursued and have made a fair bit of progress on. Okay, sorry?
It's still unreasonable to hold it.
It's not unreasonable, but it wasn't known. Yeah, which is strange, also strange to me. Okay, so here's a little more in the weeds. So if you recall, like if you're familiar with PAC learning, there's this, as I said, there's this delta parameter. It's the confidence parameter. Okay, and in PAC learning, it's very simple for how you can amplify your confidence. Like if you have an algorithm that only works with probability 1%, how can you amplify it to get an algorithm that works with probability like 99%? Does anyone remember this? Yeah. Can use a boosting algorithm. Good. That's for the epsilon. That's for the other parameter, the epsilon parameter. That's way harder. This is like super simple.
Just repeat.
Yeah, just repeat. Exactly. So you have an algorithm. It works with probability 1%. Run it, and then in PAC learning, you always see labeled samples. So just take more labeled samples and see if your classifier is doing well on the new set of labeled samples. If it's not doing well, run it again. You know, and take new samples, run it again, so on and so forth. That's how you amplify your probability of success. You can see immediately this does not work in TDS learning. Why? Because you have a classifier. You don't get labeled samples from your test set. You only get unlabeled samples. So I have no way of measuring whether or not my classifier actually worked. My point here is that even these simple things that you would like to do are actually non-trivial. Now it turns out that you can prove that if you have a TDS learner that works with probability 51%, you can amplify it to work with probability 99%, and you do take majorities of independent trials of the algorithm, but you have to argue that, and it's not super deep, but it's not trivial. Okay, so here's my sort of final puzzle about TDS learning to give you a feel for how the model works. This one's ever so slightly mathy, but I think it's a fun example. Okay. So imagine your function class are just like half spaces, you know, so linear separators. They're putting plus points on one side and minus points on the other side. And I'll tell you that the ground truth function, so f star, let's say it's the ground truth. Like there actually is a function that's labeling all of your points in both dtrain and dtest. It's labeling them perfectly. And it's the sign of w star inner product x, where w star is a unit vector plus theta. Theta is a real value. And I'll even tell you that like the training distribution is super simple. It's a spherical Gaussian. Okay, so it's like the simplest possible case. You have a spherical Gaussian for your marginal distribution. You're looking at linear separators, and you want to TDS learn this function class. And I think that the thing to think about, what's interesting about this scenario, is that imagine that you only see positive examples in your training set. Okay, so you're the learner. Remember, you get labeled samples from the training distribution, unlabeled from the test distribution. But imagine that in your training distribution, you only see positive examples. Sort of a silly example. Like if you were actually building a classifier and your training set had only positive examples in it, you would just quit, say everything's positive. But here, in fact, it seems like impossible. The problem is, imagine I see everything positive in my training set. And now I get some new points from my test set. How do I know that they're not from some other part of the distribution that should be labeled negative? Like, should I label them positive? I mean, maybe they're from a part of the distribution I've never seen before. In fact, it almost seems impossible. Like, if you've only seen positive examples, like how can you possibly make progress? You've sort of learned nothing.
But sorry,
Yeah.
if the test distribution disagrees a lot with
Do you see no labels with the test?
no, you see unlabeled examples.
Yeah. So what do you mean by disagree?
If the x distributions disagree, like
In what? Yeah, exactly. In what sense? Right, but in what sense? What should I do? But remember, I do have to accept when they're the same. So, I mean, you're right. You're onto something. Like, what tests should I do to like determine if the D prime has sort of shifted from D? That's the whole game here. Exactly. So one thing you cannot do, it's tempting to say, draw some samples from D prime. If they don't look Gaussian, just reject. But as I said, there is no efficient test to determine if a distribution is close or far from a Gaussian. Like in variation distance, you need exponentially many samples in the dimension. Even that simple suggestion turns out to be way too hard to do.
you can do respect to all the tests that are with respect to this class has this dimension D, right?
Yeah.
So can you do with respect to those tests?
Nope. You can't test Gaussianity here.
No, just for these statistics. With respect to all the half space.
Yeah. The question is, what does that mean?
Like the supreme move of it all.
Yeah, you can't compute that. Good. This is good. So let me just point out that in the case that that everything is positive, you actually have learned something. Here's what you've learned. So W star is a unit vector. X is a spherical Gaussian. So W star dot X is distributed according to just a univariate Gaussian, right? But everything I saw was positive. So what does that tell us about theta?
It's very
It's very large, exactly. So the only way that you could have seen all positive examples is if theta was super large, because you know W star dot X is distributed like a Gaussian. And so the only way I could see all positive examples is if theta is so large it's just dominating everything in the distribution W star dot X. So we've actually learned that theta is large. And now this is suggesting a test. And the test is, check somehow that D prime is sufficiently concentrated. Because if the points from D prime are also somewhat concentrated, well then I can just accept and output positive, because I know that theta is still going to dominate everything. And it turns out that algorithm works. So what you do is you check all the low degree moments. So you literally look at like expectation of x2, x3, x7 with respect to D prime. So you look at all these empirical moments of degree at most turns out to be log 1 over epsilon. And you just see, do they look like what they should be if it were a Gaussian? Like we know what they all should be for a Gaussian. There's a formula, you can look on Wikipedia for it. If they all look the same, then we know it turns out that D prime is sufficiently concentrated and that I can accept and just output positive. And that gives me an algorithm. So yeah, you check that D prime satisfies like Gaussian moments by estimating the first log 1 over epsilon moments. And that actually gives me an algorithm that runs in time dimension raised to the power log 1 over epsilon for half spaces with respect to Gaussian distributions. And it turns out you can prove something called an SQ lower bound. You can show this algorithm is actually tight. You can't do better than this, even in this super simple scenario. Yeah.
Made a strong assumption about D.
Good. I made a strong assumption about the training distribution. And I'm always happy to make assumptions about the training distribution, because if you're creating a foundation model, you have a lot of control over the training distribution. For example, when we build our protein foundation models, we subsample uniformly from a known data set. Like that assumption doesn't bother me so much because you have a lot of control over it. It's the assumptions on the test distribution when you go out to deploy it in the wild that I'm looking to avoid.
It almost sounds intuitively that you're testing distance of D prime and D, and if the distance is too large, you say reject.
Right, but
That sounds related to
right. So the point is you can't in general use tools from distribution testing to do that. It's intractable. So we have to come up with these algorithms that are sort of catered to like your learning algorithm and the function class at hand and the training distribution. Like everything has to be bespoke in a way.
It's like my intuition is correct, but not computable, and you're actually making it work.
Yeah. We're actually making it work for these other notions of distance. Yeah. And so like if you happen to care about any of these function classes, like decision trees or intersections of half spaces or homogeneous half spaces and so on and so forth. Like we have these papers that have these running times. It turns out like even for just log concave training distributions, you can get polynomial time algorithms, fully polynomial time algorithms if you let me pay like 100 times lambda plus epsilon or something. You can start to do stuff like that. And just to, in the remaining time that I have left, I wanted to give you a feel for what's involved with coming up with these algorithms. And the key, it's not too surprising, but the key is like, how do you certify that a classifier's performance on D translates over to D prime? And as I said, distribution testing will not work. Like here would be an amazing result. If you had an algorithm that could take a classifier, like I hand you a classifier and I hand you the test set and I say, just tell me, is the error going to be small or large on this? That would be amazing if you could come up with an algorithm that does that. That problem seems way, way, way too hard, Tal, to get back to your question. Instead of a generic algorithm like that, we have to use the fact that we have to couple the test with the learning algorithm, and often the fact that it's outputting like the best fitting classifier from some class in some way. So it's more complicated than that. So it turns out that one key idea to coming up with algorithms for learning in this setting is something called sandwiching polynomials, which is related to being fooled by KY's independence and pseudorandomness. And so it turns out if you have like a sandwiching polynomial, we say that a function class or f or a function f has sandwiching polynomials. If there are these upper and lower degree polynomials, pd and p up, that pointwise bound your function that you're interested in, and also the expectation with respect to, say, your training set and only your training set, the expectation of p up minus p down squared is at most epsilon. So it turns out if your function has this type of sandwiching polynomial with respect to your training distribution, that's the key thing, only with respect to train, then you can actually come up with TDS learners for functions that satisfy this particular property. And the theorem that we have is that if your function class, like imagine C is neural networks or something, has degree k sandwiching L2 sandwiching approximators, then you can learn it in time d to the order k, where k is the degree of the sandwiching polynomial. And for half spaces, k turns out to be something like 1 over epsilon squared. So you can just, you can turn a crank now. You can find like a structural property of your function class and immediately get new TDS learning algorithms for it. And the algorithm, the test itself ends up being what I was talking about earlier. You do a moment type test and check that all your low degree moments on D and D prime are the same. And then you run polynomial regression, the actual algorithm on the test distribution. So like, this is the first idea that we had, like moment matching. I don't have time to prove that it works. Sometimes I do that. It's a high wire act. And then you can ask like what classes have L2 sandwiching. So let me get to somewhat harder results. So if you just do moment matching, if you just check that the low degree moments between D and D prime are the same, you do get some subset of results. And those are sort of the easy results that you can get. And then subsequently, we have a bunch of papers that show how to come up with more sophisticated algorithms. And you can't there just rely on moment matching. You have to do more interesting things. So let me try and just give you a feel for what we can do. This result is for half spaces. They're origin centered, but there might be noise, so there might not be a ground truth function. And it turns out the algorithm is very complicated. So we have to first run SGD on some non-convex loss. This is a paper due to Diakonikolas and Konstantinos, Samos, and Zarifas. We obtain some candidate classifier, and then we have to test some like weak anti-concentration and concentration properties of your distribution using some tools from SOS, from sum of squares proof systems, so sort of a very high degree polynomial runtime. And the main thing pictorially that we wanted to test, and this is the kind of the second main idea that we have, is something called localization. And the idea is like, let's say that you have some candidate classifier V1. For any other classifier V2, like imagine there's some other classifier V2 here, V1 and V2 have an error region. That's the area shaded in green. That's the area where they disagree. And basically what we need to test is that simultaneously, for every other classifier, for every other half space, the error region, D prime, does not put too much weight in that error region. So we have all these different error regions as you rotate over different classifiers, and we have to somehow simultaneously check that your D prime distribution isn't putting too much weight on these error regions. And that intuitively at a high level tells me that, like, well, you know, for the classifier that you had, it has some area where it might disagree with similar classifiers, but the test distribution isn't putting too much weight on that region, so you're okay to deploy this classifier. And this basically involves testing various spectral properties of projection matrices that are induced by the classifier that you have, but it doesn't do like a global moment test, as I was alluding to earlier. So that's sort of one idea that we had. That leads to a notion of localized discrepancy distance, back to the definition. And so we have this. So yeah, let me get to this. Let me just say this in the few minutes that I have. So there's been a lot of recent work in relaxing the conditions under which your algorithm accepts. So we have algorithms that will accept if the TV distance between dx and d prime, between train and test, is bounded, rather than just being equal. And this is in a beautiful paper of Goel, Shetty, Stavropoulos, and Vasilyan. They use a very interesting outlier removal algorithm, and it actually implies the first set of efficient algorithms for learning in Shafi's model in the PQ model for some types of function classes. So you actually can go beyond sort of TDS learning in some cases. Yes, and then you know, another thing that this ends up being related to, sort of with regard to robustness, is learning with contamination. So it may not surprise you that sort of distribution shift turns out to be a harder problem than learning with respect to robustness, in the sense of an adversary might be corrupting your samples. So using a lot of these tools, this will appear at Colt this summer, we came up with an algorithm to learn AC0, which is a fundamental concept class from complexity theory, in a model where an adversary can come and adversarially corrupt both the covariates and the labels of your training set. This has been open for like 30 years. And we were able to use some of these outlier removal tools to get around, you know, to actually come up with the algorithm that matches the best known algorithms in the non-noisy setting. We can do some things for the regression setting. We can port kernel methods into this framework. I don't have time to talk about it. We can compose using testable learning to verify even the assumptions that we take on the training set. We can come up with universal algorithms that will accept whole classes of test distributions under very weak conditions. We have a bunch of lower bounds. Let me just say my concluding thoughts are that you know, TDS learning is very interesting because it makes use of a wide array of like very recent and interesting TCS algorithms, as opposed to kind of prior work in pack learning that was sort of stuck in a fairly narrow range of techniques. And that that we should rethink our notions of sort of pack or epsilon delta learning as not really learning, but more mimicry. That domain adaptation is a much more meaningful notion of learning. And that, as I mentioned, you know, taking assumptions often undermines you know, our goal of obtaining provably efficient results. So I'll stop here. Thanks.
So we have minus a moment for questions.
In the classic kind of like H delta H style domain adaptation, it felt like always the problem with these bounds was the trade-off between lambda and the discrepancy. Like in order to get lambda down to 0, you need really flexible function classes for which you maybe don't have uniform generalization bounds. It seems like this class of techniques give you more computable ways of addressing the discrepancy part, but maybe not that trade-off.
Yeah, I mean, even the lambda equals 0 case is super interesting.
Right.
So, and there you still run into these. I mean, all we're doing is sort of coming up with, well, not all we're doing, but we're coming up with like different ways to test like some type of metric. These metrics like H delta H, they're too general. That's the point of this work.
Right, right.
Want to yell?
Not good at that. So I was wondering, like, so there is a lot of error that may get into lambda. So, you know, like definitely one of the motivating settings here is when lambda is 0. but then lambda could be really bad. Like say in the test distribution, labels are flipped.
Yeah, exactly. So the test distribution could have all its labels flipped from the training
Right.
distribution, and there's nothing I can do. Yeah,
And you know, like I guess with the access to the information that you have, there's nothing you can do about
yeah,
that.
yeah.
But I was wondering, like, are there models where they're trying to get at, you know, what if I have a few samples from test? And, you put some assumptions on like the power of adversary flipping labels or doing stuff with.
We've thought about that and haven't been able to come up with anything like really clean. It just gets messy very quickly. Yeah, but yeah, no, but I think that's. I mean, we're still thinking about it.
Cool.
Great talk. So I'm just wondering whether you have any comment or insight on the connection between learning with covariance shift and continual learning.
Oh, I haven't thought about that. Sorry, I don't know.
Have you looked into the connection of the cases where the underlying D prime is there's some connection with the D's, for example, invariance risk minimization setting where data comes from different environment, that the causal relationships remain invariant, but the spurious ones change. So then the notion of distance, that's
Yeah, I mean, there are whole areas of like concept drift, and you know, that's more sort of into transfer learning. And I guess we felt like this was like in order to solve those problems, we felt like we needed to solve these problems first, and even these turned out to be very challenging.